Find the max rate of change in the surface function x times e to the xy at the point 0, 2 and find the direction in which it occurs. When we're asked to find the maximum rate of change in a surface, that is going to occur in the direction of the gradient vector. The gradient of f, or del f, points the way to the path of steepest descent. So this gradient vector is going to give us the direction of the maximum rate of change. And the magnitude of the gradient vector is going to give us what that maximum rate is, the maximum value of the directional derivative. And the formula for calculating the gradient vector is the first partial of f with respect to x, first partial of x with respect to y. Remember, this is a two-dimensional vector in the floor that points in the direction that we should slice in order to get a tangent line that is as steep as possible. So again, our surface function was x times e to the xy. We're looking at the ordered pair in the domain 0, 2. And so the first thing we need to do is calculate the first partial with respect to x, which means that we're holding y's constant. X is the variable. We do have a product of two expressions in terms of x, so we're going to have to use the product rule. So this will be the first times the derivative of the second. The derivative of e to the xy is e to the xy times the constant y, and then we'll add that to the second times the derivative of the first. So e to the xy is the second, the derivative of x is just 1, and so let's clean this up. So this is xy e to the xy plus e to the xy, and that's our first partial with respect to x. So now let's do first partial with respect to y, which means that we're going to be holding x constant. If x is constant, then that x out front is a constant multiple of e to the xy. The derivative of e to the xy with respect to y is going to be e to the xy times the constant x, like this. So we get x squared times e to the xy. So our gradient vector in general would be the first partial with respect to x, which is xy e to the xy plus e to the xy, as the distance that we travel in the direction of x, and x squared e to the xy as the distance that we travel in the direction of y, again in two dimensions. Now we'll take this gradient vector and evaluate it at our domain element, which is 0, 2. So plugging 0 in for x is going to eliminate this entire term, and then we have e to the 0 power here, so that's just going to be 1. Plugging 0 in for x again eliminates this entire term, so now we just have 0. And so this gradient vector is the one that points the way to the path of steepest descent. This is the direction of the maximum value of the directional derivative. What is that maximum value? Well, that's when we would take this magnitude. The magnitude of the gradient vector, in this case, is just going to be 1, and this is the maximum value of that directional derivative, meaning that the steepest slope we're going to get is a slope of 1. Up 1, out 1, up 1, out 1. So to get a quick visual of that here in GeoGebra, we've input the surface function. We are at this surface, and at the ordered triple, 0, 2, 0, which is the point in the floor that we're looking at. And this is our gradient vector. It's a two-dimensional vector in the floor. It's pointing to the direction that we need to be slicing in order to achieve a tangent line that is as steep as possible. So if we slice in any other direction, the tangent line won't be that steep. So when we slice the surface in the direction of that gradient vector, we get an intersection curve and a tangent line to that intersection curve, and this tangent line is as steep as possible, right? And as we said, the value of that maximum rate of change is a slope of 1, up 1, out 1, up 1, out 1. So the directional derivative has a maximum value of 1. That's the steepest possible slope that we could get if we slice this surface at this point.